switched on the live stream for the YouTube.
Oh, we are streaming now.
Yeah, we've got quite a few views on YouTube, so that's working really well. Live stream for the YouTube.
Oh, we are streaming now. Oh, I hear myself.
Yes,
delay.
because it automatically launches the YouTube live stream in my background, and then we hear ourselves back echoed.
Oops, let's mute R2D2.
So I see the participants are trickling in.
Actually, Ilse, can you see the whole screen, or you see this webcam screen at the bottom right corner?
I have dual screen, so I see the full screen for you.
I
mean the shared screen.
Okay.
I see only the slide.
Okay, perfect. Yeah, so Zoom is smart
on a single screen. On a single screen, I can see you as a little box to the right of the whole screen. I can see the entire screen then of yours too, and then just the active speaker.
Oh.
I do hope Javier joins because he was assigned a chair for the session, but I don't see him yet. So we're 1:30. As usual, we'll wait a couple of minutes. And I would like to ask the panelists, since we're missing the chair, is anybody willing to volunteer for this session to chair? Because I'm speaking, and I found yesterday that speaking and chairing doesn't really match.
Ilse, if you want, I can do the tech and the chair.
Okay.
Until Javier starts.
Yep. That's awesome. Thanks, Kazi.
All right. So I will put on. It's more friendly like this. So good morning, good afternoon, and good evening to all the participants. Welcome back. So we will start now with our first lecture by Ivan Martí Vidal. He will be talking about typical data issues and how to solve them with CASA. Please start, Ivan.
Okay, thank you. Thank you, Casey. And I apologize for having joined so late today. I had other things. Okay, so welcome everybody to lecture 6. I'm Ivan Martí Vidal from the University of Valencia. And well, if this talk would be related to all possible problems you could have with VLBI, I would need the rest of the week just for me, because it's such a painful and difficult technique. We all know that many different things can happen. But fortunately, we have added this typical word at the beginning, so we will just focus on the problems that usually arise in any VLBI observation. Okay, so I kind of arranged the different problems we might encounter in the observations in 3 different types. Okay, so first we're gonna discuss about the effect of bad gains. Okay, how they map into the image. Okay, what's the effect of having an incorrect or inaccurate gain in any antenna or in a set of antennas, and how the different kinds of gain errors map into the images, and ways to try to solve that, to address that. Okay, then we will talk about bad data, because the problem may not be related just to the gains, but also to the data. Okay, if the data is too noisy, the signal to noise ratio is too low, we may also have problems when trying to correct the gains using self-calibration. So we have to be very cautious about that. And last but not least, bad sources. So the data could be okay, the calibration could be okay, but the sources themselves could have some properties that make their analysis troublesome. Okay, and then we have to think well what to do and how to configure the deconvolution algorithms and so on. So let's start from the beginning, the case of bad gains. Okay. So, and we start from the very, very beginning, the very basics, okay? This you all know, okay? So I'm just gonna pass very fast through this. So as you all know, the true image brightness distribution is related to what we call the visibility function, okay? Which is what the interferometer measures, okay? We measure samples of the visibility function, okay? So that we only have a finite coverage of the visibility function. We don't know the visibility function in the whole Fourier space. We only know it in particular points of the Fourier plane called coverage. Okay, this is the UV coverage, a function that is a binary function. It's 0 wherever we don't have baseline observing, and is 1 wherever we do have a baseline observing. Okay, so this is a binary function that multiplies the visibility function. If we Fourier transform this, we get what we call the dirty image, okay, which is related with the true image via the very famous convolution theorem. Okay. So this ensures that the true image and the dirty image are related by this convolution with what we call dirty beam, okay? And the dirty beam is nothing more, nothing less than the Fourier transform of the coverage, of the Fourier coverage, the UV coverage of our interferometer. So far so good. We all know this, but life is a little bit more complicated than this ideal world, okay? In real life, what we have is that what we measure is not exactly the visibility function at that point of Fourier space where the baseline is observed. What we do measure is a corrupted version of the visibilities, okay? And this is corrupted by a function, okay, that we could call gain error, okay? Ideally, this gain error would be 0, so that the visibilities, the true visibilities and the observed visibilities would be equal. But in the general case, this is not 0, okay? So we have either amplitude or phase. This is complex valued, of course. We can have amplitude, phase, or both, combination of both things affecting the visibility function. Okay, so in the end, if we do some maths out of this, the conclusion is quite interesting. So the image that we observe is not the dirty image. Okay, what we observe is the convolution of the true image with another thing. Another thing that is not the dirty beam is another thing, is what we could call the true beam, okay? The beam that really is convolving the data because of the gain error function, okay? So actually, this is the origin of all the ugly systematics and effects that we see in an image when we are cleaning it and we have gain problems, okay? The fact that the true image and the observed image, what we would call dirty image, but it's not exactly the dirty image, it's the observed image, is the convolution of the true image with two beams, okay? The sum of two beams, okay? One of them is the dirty beam, the one that we know, okay? And another one, which is added to the dirty beam, is what we could call, let's call it the gain beam, okay? Just to be consistent with the rest of the nomenclature, okay? So in the end, this gain beam is the Fourier transform of the coverage times the gain function, okay? Well, sorry, yeah, exactly. Times the gain function. If this would be 0, of course, this would be 0, and the convolution would be with the dirty beam, okay? So in the end, what I wanna emphasize with all these maths is that the effect of a bad gain in an antenna or in a set of antenna is a convolution-like effect in the image plane, okay? So something that is being multiplied in the Fourier space, of course, becomes convolved in the image plane, okay? So what we have is that the point spread function that is convolving our data is not the point spread function that we use in the deconvolution. Both beams are different, okay? So the image is convolved with one thing, and we deconvolve another thing. We deconvolve a beam that is different from the true beam, okay? So again, wrong antenna gains have a convolution-like effect in the image plane. The true convolving PSF, the one that really is convolving the image, and the one that we are computing from the UV coverage and using cleaning, these two beams are not equal, okay? And this introduces dynamic range limitations. And you may ask, what is dynamic range limitation? A dynamic range limitation is a limitation in the contrast of an image, okay? So the amount of contrast that you can retrieve from the convolution is limited. Okay, if you have a very strong source and you have a very weak source close by, it doesn't matter how sensitive your interferometer is. If you are limited by dynamic range, you may not be able to see the weak source because of the presence of the strong source. even if you have more than enough sensitivity to detect the weak source, but you are limited by contrast, not by sensitivity, okay? Here you have a graphic example when I show this. So this is a simulation of Westerbork, okay? Observation of a source. I think the declination was 30 degrees north, okay? And we have observed two sources, one which is a very strong one that is here, and the other one which is around here, is very weak. We can't see this from the dirty image, okay? We need to decompose the beam first. So I have added an error, okay? A phase error in one of the Westerbork antennas. It's about 20 degrees of phase error in one antenna, which persists in time, okay? First, I'm gonna show the result of cleaning with the data perfectly calibrated. So you clean this source and you are able to see the weak source here. Actually, you see it very well. It's very clear detection of the weak source. But now if I add the error, if I add the antenna error, look what happens. Okay, it's just adding 20 degrees phase in one of the Westerbork antennas, only one of them. And the limitations that we get in dynamic range are enough to just wipe out the signal from the weak source. Okay, as you can see, these differences here are the differences between the PSF that I have used in the deconvolution and the true PSF that was convolving the data, okay, which was multiplied by this G function, okay? So now, how do these G's behave? Okay, so as a function of the kind of gain error that we have different effects in the image plane, different convolution artifacts. Okay, here I show you a couple of examples that we all know already. So I think I'm wasting time explaining this. So the first is the amplitude-like effects. Okay, so if the gain error function G is real valued, so you only have amplitude errors, okay, then the distribution of this is even in Fourier space, and because of the Fourier transform of a even function is even as well, the residuals are even. That means that this error PSF is even, okay, and then the residuals that you get here, the convolution-like residuals, okay, here you see the dirty image of a Westerbork simulated observation, and here you have the residuals after cleaning, okay. And as you can see, this is a convolution-like effect. So the same residuals that you see in this source are also around this source. This is the same. It's a convolution-like effect. These amplitude errors produce symmetric or evenly distributed residuals around the sources. Okay, so you see there's a kind of positive ring here, then you have a negative, then you have a positive, and these are distributed symmetrically with respect to any point source that you have in the image. In this case, we only have two sources. You have the same artifacts around each one of these sources, and they are symmetric. Okay. If, on the other hand, you have a phase error, and the phase is not very large, okay, if it's rather small, then this is pure imaginary at the first approximation, okay, and odd because of the Hermitian properties of Fourier space. Then the residuals will be odd, will be just the opposite as with an amplitude error. So as you can see here, the residuals after adding a phase error in one of the Westerbork antennas, you have here a positive residual, and at the same distance from the source, you have a negative. Okay, so you see this distribution is antisymmetric. Okay, you have antisymmetry. This can help you in some simple situations to try to guess which kind of error is affecting your image just by looking at the distribution of the residual in the image. Okay. Now I would like to ask you to answer a question. So this is a quiz, okay? Just to check how is your Fourier vision, okay? And now if this works, now Ilse could launch a poll where you have to select which, from all this antenna distribution, which is the EVN, as you all know, okay? So which baseline and which kind of gain do you think is affecting this, is producing these systematic residuals here? Do you think it would be a Jodelbank-Onsala amplitude gain, for instance? Jodelbank-Robledo? Or, yeah, which kind of baseline and gain error you think is producing this? Do you give some time for the answer, or Ilse?
Well, I will give a minute.
Okay. I hope we don't
But there is also the time pressure.
Yeah, people can also only submit the answers when all the questions have been asked. So we've got slide 10 and slide 11, but then the last question.
Okay, so just answer slide 10. Yeah, only the first slide. Okay?
Yes, slide 10.
Okay. So we will know the answer. Maybe after the talk.
Yeah, there's.
Somebody says that they cannot submit.
I can see answers dropping in now, but people
Okay.
have to think of an answer for the next one as well. So if now we
Okay.
can only look at.
Yeah, we could maybe reveal the truth here, or just give some information. Well, you see that the source was here at the middle. Okay, so the residuals seem symmetric, right? You have negative, positive, so these are symmetric. And looking at the spatial frequency here, one would say that a long baseline should be introducing this, okay? Because the spatial frequencies corresponding to this are high spatial frequencies. So that means that the baseline should be long. So that's all I can say, okay? Now, next question. It's the same array, but now the residuals look very, 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 very different. So what do you think is happening now?
Excuse me, can everybody see the poll still? Because I lost the vision of the poll, but perhaps.
Oh, I've still got it live.
Yes, I see people answering yes. So okay, that's very good.
Okay, so
because apparently people need to see all the questions before they can do submit.
Oh, that's a limitation in the polling system, yeah.
Yeah, well, but we will wait until you have finished all the questions, and then everybody can. We will see the answers all together.
Okay. So now it's very different, yeah. Now it looks antisymmetric. It looks like an odd distribution, not even distribution, right? And look at the spatial frequencies. Okay, look at the scales of the residuals. This should be a rather short baseline, right? Okay, so I'd rather move to the next slide because we are short in time as always. Well, real life is a lot more complicated. Okay, in real life you don't have just one or the other. You have combination of everything: amplitude, phase error from different baselines, antennas, times, whatever. Okay, life is very complicated in real life. So what do we do in these situations? How can we identify the bad gains, or the antennas with bad gains? Okay, one easy way is actually to take advantage of the spatial frequency distribution in the residuals. So actually, if you take this image, this residual image, and you compute the inverse Fourier transform of it, what you get is this. Okay, this is the inverse Fourier transform of this image. So basically what we have is that the only signals that we get from the residuals are of course located in the spatial frequencies of the gridded visibilities. Okay, so we only have a spatial information about the of the baselines that were observed. And as you can see here in this plot, there are some baselines that are spatially illuminated in this plot. So you have an extra power in these baselines. This is actually the information that couldn't be deconvolved. Okay, so what remains here in the residual actually belongs to these baselines. So this is the difference between the true PSF and the PSF used in the deconvolution. These are the spatial frequencies that have an extra power in the true PSF and not in the PSF used in the deconvolution. Okay, and there is a CASA task actually called checkres, which is a pretty old task. I don't guarantee it to work in the latest CASA versions, definitely not in CASA 6. And you can retrieve from the Nordic Alma Regional Center node that actually takes advantage of this. So what it does is to compute the Fourier transform, inverse Fourier transform of the residuals, and overplot the baselines of the antennas that you select. So you just choose an antenna and it will overplot all baselines to that antenna. And that can help you locate the responsible antenna or set of antennas that is producing this extra power in the spatial frequencies of the residual image. Okay, that's one way to do this. There's another more classical way, which is using the plot MS task that was described by Benito yesterday. Okay, here I show you a couple of examples of the kind of plots that you can use to find out these problematic gains. Okay, one of them would be to plot the amplitude of the residual visibilities. Okay, so look at the column here. Okay, it's set to corrected model minus corrected minus model vector. That means vector subtraction or coherent subtraction of the corrected column minus the model column. So in principle, this subtraction should produce a pure Rayleigh distribution of amplitudes. which means that the amplitude should be around 0, actually around the RMS of the baseline error, or the baseline noise, sorry. And as you can see here, there are a few outliers which don't follow this distribution here, okay? So for, now just selecting a region around each one of these colors and just pressing this magnifying glass, which is the locate button, you could identify the responsible baselines that are off of the model, okay? Just by plotting the amplitude of this coherent subtraction of corrected column minus model. Another plot that can be useful, but can have problems if your source has a rich structure and you have nulls in Fourier space, but if that's not the case, this is also useful, is to plot the phase of the ratio of visibilities over model. Because when you divide the model by the, the visibilities by the model, what you do is a kind of the convolution of the source using the source itself, okay? So what remains after this ratio should be 0 phase for all visibilities and a constant amplitude, okay, for all visibilities, for all points in UV space, okay? And as you can see, here we have 0 phase for a good fraction of the baselines, but there are all other baselines that are offset in phase, okay? These small phases of 10 degrees minus 10 degrees that you see in some baselines are produced by differences between the PSF used in the deconvolution and the true PSF, okay? So these are two ways that, of course, there are more combinations, but I just tell you the two, what I think are the two most interesting ones, or the best ones to check for outliers in the residual visibilities, okay? So what would tell you about the problems in the gains. So what do we do when we find these problems in the data? We can do two things. One is the Richman approach, which is just flag the data. Okay, you forget about them. If you have many antennas, you can do this. The other one is the Pullman approach, which is usually the case in VLBI. You can try to keep them, okay, and you can to sanitize the data, okay, by using self-calibration. Self-calibration is just deriving antenna gains that reproduce or minimize the difference between visibilities and model, which is mathematically similar to just minimize this extra power that you see in these pixels here, okay, so that the residuals become more Gaussian-like, more noise-like, okay? So self-calibration and iterative hybrid imaging would be the answer, okay? We use this to correct these bad gains. This is a powerful tool, very, very powerful tool, but as all we know, a great power comes with great responsibility, okay? So self-calibration is very powerful, but you have to use it with a lot of caution, and I mean really a lot of caution, because you can cause very odd things to your data if you are not cautious enough. And that brings us to the next kind of problems. It's the bad data. And you know, bad data is worse than no data at all. So don't play with bad data too much, because you may end up arriving to completely wrong conclusions, okay? What happens? What do I mean by bad data? I mean noisy data, okay? Data that are too noisy in order to be used in a self-calibration, okay? So in principle, if the calibration is correct, the real and imaginary parts of the visibilities have Gaussian noise that is uncorrelated between them. So real part has its own noise, imaginary part has its own noise, and both are uncorrelated. This is in the ideal world that the calibration is correct. And of course, if you translate this to amplitude and phases, you get completely different things. The noise is not Gaussian anymore, and you have correlations, okay? So working in this space is very different than working in this space. The problem is that self-calibration works in this space, the space that's right, amplitude and phases, where the noise is not Gaussian and you have correlations. And these correlations can cause a lot of trouble, okay? Actually, this brings us to the next and last quiz question. So that's the third question in the poll. Okay, so here you have a distribution of this is time evolution of the visibilities of a given baseline. We are observing a point source, okay, and this is what we get in a given baseline of our interferometer. And now the question is that we are observing a source which has a given flux, okay? We have here flux 1, flux 2, and flux 3. Now the question is, which flux do you think is the right flux of the source? By looking at the amplitudes and phases, looking at the visibility plots here, what do you think is the right flux density of the source? So do we give maybe 20 seconds, 15 seconds to think?
Yes, until now 20 seconds.
I'm very curious to see the answer to this.
It's almost equal.
It's
Although
moving.
there's a slight preference for the bottom red line now. So people are still voting. I still see numbers trickling in.
Okay, yeah, now there was a large increase. Well, 10 more seconds.
Da-da-da-da.
And then 5, 4, 3, 2, 1. Closing votes.
Yes.
And poll.
End of votation.
So now,
Oh, here are the results. Okay, yes, this one was correct. This one was correct, yes.
Could you maybe go back to the slide you referred to when you discussed them?
Shall I come back then?
Yeah, just quickly go to slide 10 so that
Oops.
people who didn't get it right understand why.
Okay, so let's come back to the poll. So you see the poll here?
no, we just see a black box hovering over.
Okay, so slide 10. So the answer was Shanghai Robledo amplitude gain. So if you look at the baselines here you have the antenna locations, okay? All options that have an amplitude gain, which is this one and this one, are very different in baseline length. So Jodrell-Bank-Onsala is a very short baseline, which produces very low spatial frequency signal in the residuals, okay? So that we would need to have a very wide residual, okay? Not a very high resolution or high spatial frequency one, but a very low spatial frequency one, okay? So the only option left was Shanghai Robledo, which is the longest, or one of the longest baselines that we have here in the east-west direction, actually, which is where we actually see the structure of the residual, okay? So that's the reason, okay? It's amplitude because it's evenly spaced with respect to the source location, and it's a long baseline because in units of the synthesized beam, which is actually of the order of the size of these waves, okay, tells us that it's coming from a very long baseline, okay? I don't know if I explained enough or we may need some extra discussion. We can discuss about this in the question.
If people have questions, they can then put it in the, question box.
So the second one was Jodrell-Bank-Westerbork phase gain. So obviously it was a phase gain because the source was here, so the residuals are antisymmetric. It means a phase gain. Okay, and the baseline now is short, okay, or it's, well, we have actually other waves here, but the one that is dominating has a very low spatial frequency, which means that it's a short baseline, okay? And the only one that matches from all these four options is actually the Jodrell-Bank-Westerbork phase gain. Okay, that's it. Now, if we come to this slide, so the answer is actually flux 1. Okay, it's very it's very tricky. Huh? I've seen people self-calibrating and fighting to the data until they would bring the recovered flux density to the green level. But that's not the wise thing to do because you always have to look at the noise in the phases, okay? It's not only the noise in the amplitudes, but also the noise in the phases what tells you whether you can recover the whole flux or not, okay? So this observation is dominated by noise, not by the flux of the source. So a good fraction of the signal here in the amplitudes is due to noise. Okay, the source only contributes a very tiny fraction here. And the way we know it is because the phases are very, very noisy. Okay, that's something that, well, we have to learn by trying, okay, and by playing. Actually, the danger of trying to put the flux into the green level is that we are generating fake noise. We are generating spurious signal from self-calibration, okay? There was a paper a long time ago, actually a very long time ago, and now I realize, oh my, I'm getting very old, where we actually studied the amount of spurious flux density that you can get when self-calibrating noisy data. And the results were awesome. So you can recover a good fraction of the RMS noise, which is the green line here. Okay, you can recover a good fraction of the green line of a spurious flux. So this is just noise converted into signal, which is a function of the integration time of the self-cal solution and the number of antennas. Okay, so for the case of very low number of antennas, let's say 9 or 10 for the VLBA, just using an integration time of a few seconds per self-cal solution can originate or create half of the RMS noise. So you can basically recover a source like the red one just from pure noise with no problems. Even with the VLBI, even having 10 antennas. So you have to be very, very cautious. Okay, this would be the equation that gives you a rough estimate of the amount of flags that you can recover from noise. And just to give you a graphical example of this, which I think is very fun, let's take an EVN observation. This is a simulation of the EVN observation of a source with 30 degrees declination, observing just noise. So I have just simulated pure random noise, no source at all, okay, during 6 hours. And now I have introduced a model. Imagine I was observing a gravitational lens and I have a nice image in the optical. I want to recover that in radio, and I start to put windows and self-calibrating. Okay, in the end, I arrive to something like this. Okay, look at the dynamic range that we are getting. Okay, so we are having a peak of, let's say, 0.05 Janskis per beam here, whereas the RMS is of the order of a millijansky. Okay, so we have a dynamic range of about 50 just from pure noise. Okay, and I have a nice gravitational lens shape here. And actually, what I was trying to recover was a pirate. Yeah, you see here the smile and the eye and the other eye here. Okay, so you can recover a pirate just from pure noise, just using self-calibration. So that's what I mean when I say that great power comes with great responsibility. We have to use self-calibration with a lot of caution. Okay. Now, last but not least, bad sources. You can, well, Ivan, what do you mean by bad sources? Okay, even if the data is correct, the way you treat it can also produce systematics. Okay. One of them, which happens when if your field is very wild and you have many sources, or you have a very large source, okay, is smearing effects. Okay, so you can produce smearing effects by averaging your data, either in time or in frequency. What happens is that basically you have a convolution-like operation in Fourier space. You are substituting tracks by points because you're averaging in time. Okay, so a track of a baseline track, you are just collapsing it into a single point which you average in time. Okay, this is a kind of convolution-like effect in Fourier space that maps into a product-like or multiplication-like effect, the image plane, which basically smears out any signal far from the phase center of your correlation. Okay, just to give you an idea of this, the importance of this effect, it limits the field of view in arc seconds by this amount. Okay, so for baselines which are transatlantic, let's say 1,000 kilometers, you have just using 11 seconds of time 1 second of time averaging limits the field of view to 11 arc seconds. Or if you use you have observations at 1 gigahertz bandwidth or like 5012 megahertz bandwidth, and you collapse everything into one channel when you clean, you are basically limiting your field of view to 5 arc seconds per megahertz. So even much smaller if you have a wide band. Imagine that's amazing. It's terrible. Okay, the field of view is very much limited. Okay, so actually one way to avoid this bandwidth smearing, if you have a very wide band observation, is to clean in what we call multi-frequency synthesis mode, where instead of collapsing the visibilities radially to one point per visibility, what we do is to perform a Taylor expansion of the source distribution, or reprojecting each visibility in its right place in UV space to try to minimize this. Okay, these are the different approaches or different strategies that we can use. And just to finish, here I show you an example where we see graphically what happens when you observe a source with a very wide bandwidth. Okay, and the source has spectral effects. So you have spectral effects in the source. Okay, I have simulated a core jet structure where the core has a flat spectrum, and this jet extension, the point here towards northwest, has a steep spectrum. This is typical in VLBI. It's an AGN. Okay, it's an AGN jet with an optically thick core. Okay, but if the fractional bandwidth is wide enough, it can happen that if you deconvolve without taking into account this spectral dependence, you end up having an image which is very noisy and very much limited by dynamic range, which would be the red contours. Okay, the red contours are very noisy. Okay, you are barely recovering the two components with a lot of noise around. Okay, now if you tell Clean to account for possible spectral dependence of the source components, which is again is called multi-frequency synthesis cleaning mode, okay, which is implemented in CASA, you end up having the white contours, okay? The contour levels are the same. I have set exactly the same contour levels for the red and for the white. The only difference is that the white image is cleaned with this MFS mode, okay? That allows you to take into account possible spectral effects in your sources. This may become especially important in modern VLBI arrays where you have wide fractional bandwidth. So we may start to see these effects of the spectral structures of the sources, and we may start the need of using this multi-frequency synthesis cleaning mode in VLBI in many cases, okay? And I think that's everything I have. So this is the summary. Images are limited by UV coverage and by antenna gains, okay? And both have convolution-like effects, okay? Both produce their own PSFs in the image, okay? The UV coverage and the gain error function, okay? This also introduces its own PSF into the image, okay? Which produces limitations in the dynamic range of the images. If there is an incorrect calibration, it is possible, fortunately, it's possible to identify the bad gains from the residuals, okay? Either Fourier transforming the residuals and trying to find out where the spatial frequencies where we have higher power in the residuals is check res task for CASA that you can download. It's an old task, okay? So I don't ensure it to work. But if you are interested, I could upload an updated version of that task into the wiki. If you like the task, or if you like the idea, okay, I could update it and upload it. And also, you can also check the residual visibilities using the plotMS task. Sorry. And you have different combinations here. Either you can plot the data over a model and look for the phases and constant amplitudes, or the coherent subtraction of a model from the data and then look for the amplitudes, not for the phases, but you can only look for the amplitudes if you do that, if you do this coherent subtraction, okay? Once bad data are identified, we can correct them with self-calibration, but again, remember, if the data are too noisy, you may not have the chance to do this, okay? Otherwise, you will run into severe problems, okay? You will introduce spurious sources into your signal. And even if the data are perfectly calibrated, you can still introduce artifacts, okay? If you perform too heavy averaging, or you clean in a mode that does not account for possible peculiarities in the source distribution, for instance, spectral effects in the source. And that's it, the typical slide to thank our sponsors, and thanks also to the organizers for giving me the opportunity to give this talk, and that's it. Thank you.
Thank you very much, Ivan. This was a spectacular talk. I really enjoyed it very much. So there's already 2 questions in the Q&A box, and I presume that there might be more questions coming in through Mattermost. I start with the first one from Miguel Perez Torres. What are the assumed frequency and bandwidths in the simulated core-jet structure of the last slide?
Okay, so it was half a gigahertz coverage in, if I remember well, what C-band. I can share the scripts, so you can reconstruct the images if you like. So imagine just having 0 and -1, just half a gigahertz over 5 gigahertz, okay, band C, and having half a gigahertz wide, which is possible nowadays with the EVN, right? With the EVN, you can observe with this spectral configuration. And you see that you start to see effects of source spectral, of the source spectrum in the clean.
Do you think that with the future brand receivers, which would be really a number of gigahertz, that we would also need to use the end terms parameter in T-clean?
Yeah. Actually, this was already using these end terms. I was setting end terms to 2 in order to fit for the scope size. For the image at the fiducial frequency plus the first Taylor term. Yeah.
Okay. Then there is a second question from Carolina Casadio. Regarding your warning in self-calibration and the example you gave with the pirate, what about if you have observed the source at 2 frequencies and at the highest frequency you don't see it, as in your case of noise dominated? Would you trust to use your model you get from the lower frequency and then self-calibrate in phase using a longer integration time?
That's a very good question. very good question. What I would do is to maybe make an analysis similar to the one that was done here, for which we basically took a data set and applied self-calibration with different integration times, okay? And then we saw how the recovered flux was decreasing with integration time. If you see that as you increase the integration time, you tend to a constant, I mean, you saturate your self-called recovered flux, then you could model this as a way of saying that this is the true flux, okay, which is independent of the solid solution, okay. Whereas if you use too short integration times, you're introducing a spurious flux to the real flux, okay. There are actually in this paper, I think there are a couple of tests or a couple of suggested tests that you can do to the data in order to check whether you have a real signal that you can decouple from the self-called spurious flux. So I would suggest to make in that case, which is a very critical one, I would suggest to make some testing to be sure how much of that signal you would trust and how much you could assign to effects of self-calibration.
Okay, that seems a clear answer. Then there is, I see, yes, the Carolina said thanks. So I think also to her it was clear. Then we have another question from E. Yoon. How often does VLBI observations have baseline-based errors, in brackets additive errors?
Oh, well, this I haven't mentioned. This is, yes, well, these are what we also call non-closing errors, okay? That's a very wild area of VLBI, okay? I would say that for standard arrays like the EVN, where the geodetic locations of the antennas and the correlation procedures have been so much tested and commissioned, baseline-based errors should be minimum, if any. So I wouldn't care much of this kind of errors for arrays like the EVN. For more state-of-the-art arrays, that can be another matter, okay, of discussion. But yeah, for the EVN, I think they would be, well, maybe Benito or Ilse or whoever is working actually at the level of being at the office close to the correlator can give you more precise information. But I don't think it's a big issue.
Benito, if you are there, if you want to add something, please do.
Yeah, as far as you know, I will say the same as Ivan already mentioned, I think. Or at least not in the general case, you wouldn't expect highest ones.
Yeah, we had a brief discussion about it this morning, and I think it was Michael Janssen who mentioned this, that for arrays like the EVN, and the baseline-based errors are basically negligible. But if you have an array like the Event Horizon Telescope, where you have a really sensitive central system like the ALMA-phased array, then it's something you need to be aware of. That might be an issue.
Okay, so we are looking still for more questions. See, all three in the Q&A box have been answered.
Yep, I don't see any.
The matter most, there is a number of compliments for the talk, but no more questions. Well, people may always put their questions when they come later on in the Mattermost box, but then I suggest to take a short break and start again at 14:30 UT for the talk about the Jupyter Notebook processing. Is that okay?
Yeah, sounds like a plan. So everybody can grab themselves a drink or a snack.
Yeah. Thank you again, Ivan, for the very nice talk.
Thank you to you.
It was very nice. And the polls were excellent. I think it's very nice.
What fun.
Yeah, the last one was a tricky question, huh?
Oh, yes.
You could see that there was the other ones had a clear preference. You could clearly see that most of the people had it right. The last one.
Yes, and it's tricky because you start to self-calibrate because you trust that you could reach that level, and then you introduce the spurious noise. So, wow, it's very dangerous.
Mm-hmm. Oh, I see that your office mate is watching. Oh,
yeah, actually, yes, we have infinite screens now.
I saw on the MetaMost that people were calculating the distance between you and the Zoom center as about 1,500 kilometers because the delay in his slide changing and user slide changing was a few seconds.
Experts.
Okay.
I will go and get a tea.
Yep.
Bye. Well, I continue here. But bye.
right? So it's almost, I have to look in the UT column, almost 14:30 UT. Ilse, are you ready for the talk?
Yeah, I'm good to go.
Okay, so then the next talk is going to be given by Ilse van Belmont from Jive, our organizer. She's going to talk about the Jupyter notebooks and the EVM pipeline. Ilse, I will give you 5 minutes warning.
Yeah. So just to inform you, Kazi, at the end of my presentation, I'll hand over to Olga for a quiz. So you're using the Slido quiz setup that we used at the start. Olga showed at the start as well. And given the timing, I should be about 35 minutes in the presentation and have 10 minutes left for that.
Okay, and we do the questions after the quiz.
Then we can do the questions after the quiz, yes. So, well, thanks everybody for still being around. We're about halfway through the lectures at this time. I'm number 7, and we have 13 lectures, but we've got a few events coming up still tomorrow. So today and yesterday, we've been talking a lot about the why and what you can do in CASA. And then several people have demonstrated the tasks that you can use. But I frequently find myself stuck in really apparently very simple things. So part of this lecture will also address where do you find the data, how do you actually get them, and what do you check in the data processing steps and the output that CASA gives you. And I will demonstrate all this using the Jupyter notebooks that we've been developing and the EVM pipeline that we are starting to implement in this environment. So first, a little step back. We're at Jive here, Joint Institute for VLBI, ERIC. You can forget what the ERIC stands for. And our core business is operations of the European VLBI network. And that is a very wide concept. So we do support everything from the step that you come up with an idea. So you propose an observing run, a target or a schedule. We help you with the scheduling, the planning, everything up until the end where we actually check your data, make sure that things look the way you would expect them to. And then we hand you the data as BI, and it's up to you to distract your science from it. This whole chain is supported in part by the EVM pipeline that's developed many years ago in Abe's Parseltongue. But as you know, and as you see this workshop, we are moving into the CASA operations time. And one of the plans that we needed to assess is how are we going to make a pipeline in CASA? This is also very helpful for new people. If you've not done any radio astronomy before at this stage, you would go to one of the bigger radio astronomy schools like the NRO Summer School or the ERIS School, which we had last year in Gothenburg. Then you would learn a lot about CASA, but APES is really no longer discussed in too much detail. So for the VLBI, we really need to make that step so we can attract new people, have young users use the instruments and optimize the functionality for us. Okay, that's the wrong one. So what does the EVM pipeline do exactly? So this is only a snip out of all the steps that Jive does with your data. Actually, this starts at the point where the data comes out of the correlator and has been first quality checked by the user support staff to make sure that there's no clear technical issues that come from back-end problems at the telescope or a cable missing, whatnot. We start at the conversion of the data format into a format that we can actually read into the software. So for APES, this would be a UV-FITS format or APES visibility format, where you use the FITS IDI files from the correlator, from the archive to import. And in CASA, you convert into the measurement set. And then basically the same steps are followed. You do the flagging, you do your gain calibration and fringe fitting, and your bandpass calibration. And at that point, your data is ready for imaging. At this stage, we're not going to discuss the imaging step in too much detail. There's lectures for this specifically tomorrow. And also in the implementation of the CASA pipeline at this stage, we're really not at the point where we have implemented the imaging yet, mainly because it requires quite a lot of interactive processing, which is not ideal in a pipeline step, but also because this was already tricky enough for us to handle. But we're getting there. We basically have a beta version of this pipeline in CASA running now, and we've constructed this in the Jupyter Notebook environment. The reason that we picked the Jupyter notebooks at this point to implement the pipeline is that they are very helpful in explaining what you're actually doing. So if you look at the Parseltongue pipeline that we are running, it's consisting of a lot of scripts. It's not always clear which steps are done. Once you get to know it and to know what it does, it allows you some flexibility in skipping steps or doing steps twice, but it's all scripted and it does have a fairly steep learning curve. In the Jupyter notebooks, everything is still linear, but I'll show you later on how you can repeat steps quite easily. And with the explanatory text, it's always fairly clear what you're doing. And if you do prefer scripts, you can easily convert a Jupyter notebook to a basic Python script. We're now developing the EVN pipeline under version control. That also means that if something goes wrong or people have suggestions, we're really starting to make this a serious development effort. We can implement new requests, feature requests, fix bugs, everything as a proper software development project. The really nice thing that I really prefer about the notebook environment is that it allows you to do both the data processing and the quality control in one step. Well, not exactly one step, but in one basic script. So as you will see, you can do your plot-ms tasks after an apply cal and immediately see if the data looks what you think it should look like. But just by itself, the Jupyter environment is not sufficient because we need a Jupyter environment that also has CASA included. And this is work that's been done by Art Kijmpema at Jive over the last couple of years. He has been developing the Jupyter CASA environment. And this is now all hosted in a container. You can either use a Docker or a Singularity container. Since I'm a Mac user, I use Docker. Singularity for Mac is, I think, still in the beta release. And the really nice thing, and I know that several of you will already appreciate this at this stage, is you get everything in one. So all your CASA and your associated Python versions are matched. You've got your VLBI scripts in there, the Python libraries. And if there's additional functionality that we need, this can be implemented in the container. The really nice thing about this is once you've done this properly, you set up your notebook and it works, you don't need to make your site the typo ever again. It's something that I run in frequently when I do command line CASA processing. You type something, you mistype the name of the command or mistype the name of a file. Of course, in scripts, you've got the same benefit. But the main thing here is also that you do not need to bother with any path settings. And I've seen already quite a few questions about this, that your libraries are not there or your path settings are not correct. This is all taken care of inside the notebook and you don't need to worry about this. So to give you an idea of what we're implementing, this is the scary bit of my presentation actually. I'm now going to show you first a flowchart of all the steps that we got in a notebook. And I will give you a semi-live demonstration of how you get all the stuff in there yourself. So I'll stop sharing my presentation and start sharing the browser, which I was looking for. Share. So first, yeah, this is all set. So this is a standardized flowchart that we've been working with to implement all the steps in the pipeline. And you can see here on the left side, it says calibration and the lower bar says quality control. And if I would scroll down a little bit, there is the imaging steps as well, which have not yet been implemented. This is the reason why they're separated. So we start here with this little circle, which is where the correlator is done and the data are archived in the EVN archive. And we start with the import step. We run our metadata scripts, the VLBI scripts that Mark has developed. And at this point, you could do already an initial inspection of your gain curve and system temperatures. Typically, then you would import this. So if you would do this from the command line, this arrow here is the point where you launch your CASA. In the notebook, you don't notice that difference. So you've got imported data into a measurement set in CASA, you inspect the contents of that measurement set, and you go on to generate the CASA calibration tables for gain and system temperature. So we'll move a little bit to the side. You can, at this stage, also plot your gain curve calibration tables or your system temperature calibration tables. You can even edit them or smooth them. These steps are currently not in a notebook, so there's no associated quality control here, but that can of course be added. The next two blocks are flagging, and they are separated in manual and automated flagging, mainly because the way that we currently do this is still mostly manual. So you have your flags that have been added to the EVN archival data, which you need to apply. I refer to this as manual flagging because these flags have been collected by the telescope operators and the user support staff into a file, a human readable file that you can apply to your data. We are experimenting at the moment with the automated flagging. For example, the AO flagger has been mentioned several times. At this point, the experiences are somewhat mixed, and we need to get in touch with the developers there to see how we can optimize this for VLBI data processing. The really nice thing of having automated flagging is that you take away all human bias that you might have if you see something and think it's nice. You want to keep it even if it's noise. If you want, you can even introduce data signals in your data that are not real. So removing that bias is something that's interesting. And also with increasing data sizes, it gets more and more tedious to do this by hand. You really want to automate that. So what I do at the moment myself, I do the manual flagging, but I do keep a log of the flags that I have applied and eventually make that into a flag file that I can apply. So every time I repeat a particular data processing for an experiment, I reapply that particular flag file. So that's perfectly repeatable and I don't need to do things again. So this is a bit tedious if you do flagging in PlotMS. But what I usually do is note down the flags that I see in PlotMS and transfer them to that file. So bookkeeping here is definitely important and somewhat problematic even. After you're happy with all the flags, you start with your what I refer to as the hardcore calibration steps for the visibilities and the instrumental delay correction. And you may have heard several terms for this flying around. It's called manual phase cal. It's called single band delay correction. It's called instrumental delay correction. And I refer to it as instrumental delay correction because that's mainly what you're correcting for errors in the instrument that arise from all sorts of effects, but which do not vary or not vary too much over the time of an observation. You do your multiband delay fringe fitting. So this is where you start fitting the delays and rate as a function of time using your phase calibrator. And when you're done, you apply a bandpass calibration. And all these have several quality control steps associated with them. You can either plot the solutions directly for the bandpass or the fringe fitting calibration tables, or you can apply them to your data and inspect the calibrated data. This is more tedious because the apply cal step is not the fastest one, and for large data sets, this can take some time. But once you're happy with all your calibration tables, you apply all of them to your data, you split out your targets and calibrators, and then you're basically done with your visibility calibration and you start your imaging. So what would you actually start doing if you are a user and you would want to have a look at an archival data set of the EVN? First thing you do is that you go to the homepage. And on the Jive homepage, there is this block that says EVN Data Archive, and it gives you several options to address the archive, to find it. So the archive home looks like this. You need to know your experiment number, and then you can type it here or select it from the drop-down menu and look what's in there. If you know, for example, the PI, but not the experiment number, you can use the browse catalog option. So you can select here whichever variable you want to, which observation period, and then submit the query and it will find it for you. Most astronomers, when they are looking for data in the archive, however, will know that they're looking for a certain source. And that's where you have the search archive function. So these options are all under this Jive EVN archive button on the Jive main page. So here is the tool where you can actually add a source, select which kind of data you're looking for, and see if it's present in the archive. This is very helpful also if you're preparing an observing proposal to check if this source has already been observed before. Now let's check this particular session. As I know this interface best. And let's select a data set. So in this case, I will select N14C3. What a surprise. So you get already on this little side window an overview of what's in the data set. But of course, you would want to go and download some data. So you show experiments, you get some blurbs about the data, but where you want to go initially is to the FITS files. The FITS files are the main visibility data set, and in this case you see there's two, RDI1 and RDI2, and there's this convenient line here that tells you what you could type into your terminal window to download the data. So you can copy and paste that, and then just sit around and wait until everything is in your machine. Besides the FITS files, you also need the metadata, and you can find this under the pipeline button. The pipeline has a bunch of products that it produces, and you can see here the list of all the stuff that comes out of the pipeline, the APES pipeline. If you're a PI of an experiment, this is where you should go and start checking what has actually been done to your data. Make sure that you understand what you're looking at. For this particular case, we're looking only for the metadata, which is under the associated EVN calibration. And I hover over this. It's probably not readable for you on the screen, but now it pops a little window under my mouse that says that there is an untap file associated with this. So I want to download this particular file, the n14c3.untap. And I also want the flags that have been applied in this pipeline. These are the flags from the logs and the stations, and they come in a file called n14c3.uvflag without an A. So these are the two metadata files that we start our tutorials with, which you can download from the EVN archive. And every data set that you find has these associated with them. And in some cases, if you've got spectral line data, you will see a little note here that tells you that there are several correlator passes, pass 1 and pass 2. And pass 1 is usually your continuum data processing, and pass 2 is the line data. So in that case, also for the FITS files, you will get a bunch of FITS files where the IDI numbers are consecutive, but this one here, just before the dot, then has 1 or 2, which is associated with the correlator pass. So that's where you find your data. Now, if you wanted to process this in a notebook, you can download any of the template notebooks and hopefully successfully install the Jupyter environment and launch it. If you can't, then on the slides that I shared, there is a link to the Jupyter Notebook Viewer. The notebook viewer itself looks fairly basic. It looks like this, and it gives you a little window where you can copy and paste the link to any notebook, type Go, and it shows you what is inside that notebook. So this is the tutorial for the N14C3 run, and I'm going to show you my own personal notebook, which has been running live, just recently been changed. So I'll go through the notebook and show you some interesting features that you could keep in mind. This is not just particular to the notebook. This is also possible if you're running this CASA from the command line, and you will see the same outputs. But already here you see that the nice thing about the notebook is that you have a little bit of text on top explaining what it is. Add some links, you can add some figures, and then people can immediately find some references for the data. So if I was a user support scientist and I found something really peculiar going on in this particular experiment, I would probably make a note here saying, look, in scan such and such, there's something weird going on. Please check if the data is still useful, or otherwise flag that scan. So the first cell that you get around, this is a code cell. Will actually give you a lot of basic information about what is the useful scans for this particular observation to do your calibration with. If you're having a new experiment, you won't know exactly what to put here. You will not know for sure which scan contains your fringe finder source. You don't know which field contains your phase calibrator. So you can leave it empty, perform the first few steps, and then from the listops file that you generate, you can fill in these values. Interesting thing to note here is that for the reference antenna, I've only selected Effelsberg, and in this case, we know this is sufficient. But if you would want to change this to a list for the fringe fitting to take another antenna when there is no Effelsberg, you could add, for example, Westerbork here, or Jodrellbank, or Onsala, and this list will be taken by fringe fitting. And when the first antenna is not present, it will jump automatically to the second, then to the third, until it runs out of that list and nothing is available, and then it will crash and tell you, I didn't have a reference antenna. So below this line here, a lot of things are set for the notebook to run. And then the pre-calibration steps start. These are the steps that include all the VLBI scripts from Mark. So the appendices is done here, conversion of the flag table and the gain curve. And then where it says number 5 here is where you do the import fits IDI. Number 6 is notable. That's where we apply the first flag, the UV flags. At this point, I also do a flag manager run to rename the flag versions to a sensible name, so that when I start from scratch, I can just clear out all my calibrations, restore the flags to only the flags that are from the archive, and start from there again. So this is the output from the list ops. The list ops, I'm not sure if this has been discussed in the first lecture because I've been doing some organizational stuff in the background. The list ops is extremely useful to show you where all your sources are, which scan has which source, which time range it was observed. And you may have noticed that at the top, I selected scan 37 for one of for the single band delay fringe fit, the instrumental delay. And the time range of that scan is actually 3 minutes, sorry. In some cases, it helps to not have the full scan, but just select the middle part of the scan. So the edges of the scan can sometimes generate a little bit more noise in your fringe fitting. So in that case, you would give it a time range instead of a scan number. And you can find all that information here. If you scroll all the way down to the bottom, it also tells you a little bit about the field codes that you have. So field 0, you should be aware CASA is always 0 based, is one of your calibrators. 3C345 is field 1, etc. You've got your spectral windows here, the number of channels, channel width, and the correlations that are present in these channels. So we have 4 correlations, all the cross correlations are there. And you can see the 8 consecutive channels with their central frequencies. So this is always very helpful information to know what to expect when you start plotting this in PlotMS. You can immediately see if this is sensible. So once we've got all that checked, we know which scans we want to use for what calibration steps. You usually start with generating the system temperature and gain curve calibration tables we've done in these steps. And you can check, for example, here for the system temperature, what the log says. This is the output that you normally get in your CASA logger. So it's not just a notebook thing, this is a CASA thing. And you have loads of warnings here. This is all points where the system temperature does not exist. So there's data points there, visibility data points there, or it expects visibility data points, and it's expecting a system temperature, but that's not there. So what will happen in the apply cal step is that if there is any data, for example, here for antenna 3 and spectral window 1, it will be flagged. Usually this is rather benign, so you don't have to worry about it too much. You can, of course, always do a plot cal or a PlotMS plot of your system temperature to see if there's really big issues there. So in this case, what I did, just do an apply cal of the system temperature and the gain curve and see what that does. Well, to your faces, it doesn't do too much. You still see quite a lot of noise. But for the amplitudes versus frequency, this is the uncalibrated amplitudes. You see similar fluxes, gains at this side, but fairly small numbers as a function of frequency. So here's your 8 spectral windows. This corresponds nicely to what the list ops fan said. And now after the gain curve calibration, you see that the fluxes or the gains are starting to see around 1, except for this orange one here, which is definitely a lot higher. So it's immediately something that you would want to check in PlotMS, which telescope are the orange points. This is one of the disadvantages actually of the notebook environment. You don't have the locate button here. So what I usually do is have a CASA running on the side where I can immediately check for this particular measurement set, if I make that plot, which are the orange points, and do I want to flag those or not? So that's where we get to the flagging steps. For some of these data, I already know that this is bad. So for Svetlo, for example, I know it's bad. For heart-based hook, scan 62 was bad. And here you can also keep a record of all the flags that you apply to your data as you are adding them either in your plot.ms or other structures. Or you can make a file, or you can keep them here, that's up to you. A thing to note for VLBI specific data processing, we always flag some of the edge channels. So we have 32 channels in this data set. Typically, you would flag 10% on either side. This is the bandpass drops off so steeply that you will not get any sensible solutions for your fringe fitting calibration there. In this case, I also flagged the first 5 seconds of every scan. And usually the autocorrelations are flagged during the correlation, but it's not always the case. Sometimes they are kept. And in that case, you could do an AC core if you need it. But at this particular step, we don't go into that detail. So again, here is a flag manager step to save a flag file or a version of my flags. Depending on your taste, you can make this a file or a flag version inside the CASA flags. And then if anything goes wrong with the calibration that follows this step, I restore this flag version and start from this point. So these are corresponding essentially to all the blocks that I showed you in the flowchart. We get to the fringe fitting now. And here what's interesting to note is the output from the fringe fitter in the CASA log actually does have some useful information. So if I would scroll down, you start to see all these signal to noise values. So this is spectral window 0. All your antennas are here for both correlations, the RR and the LL. Never know which order they are. And you see that we've set a threshold of 50, but in this case, antenna 9 has a lower value than 50, which means the solutions will be flagged for this one. What is good to know is that for most of the antennas, all the values are high, which is what you would expect for a fringe finding source. And the least squares converges in only a handful of iterations. If this should be a very high number or an exact round number, you should start to get worried. It usually means it hasn't converged and your solutions are not sensible. So you would see that these outputs occur for each spectral window. And then at the end, you see an overview of each spectral window. And there's all ones here. That means that it has successfully found solutions for each spectral window. And your day is good. So if you apply this instrumental delay correction to the scan that you used to derive it, we've been seeing this a few times already, you see that the phases are all nicely lined up. There's no phase jumps and they're all around 0 degrees. And you see the difference here. Some phases have a little wiggle in them and some are straight. And this is the difference between telescopes with a digital backhand receiver and an analog backhand receiver. And it's something that you in the end can correct for with your bandpass calibrations. The CASA bandpass provides a complex bandpass. Now this is only for the scan for which you did your instrumental delay correction. If you look at another scan, you see that the phases nicely line up, but there is a slope. Again, especially for the longer baselines, this will be obvious. The slope is there because you're looking at a different point in the sky, different time as well. Also here, the wiggles and the straight lines are more obvious. So after we're happy with the single band delay, instrumental delay, we go to our multi-band delay. Well, you've seen all the settings in for this in Des's talk, so I won't go into detail. I'll just show you here a different way to inspect your solutions. This is actually the plot cal task. So I'm plotting here the delay rate as a function of time and the delay as a function of time. Now this looks a little bit weird. It has a few points which are off. So you can either inspect which stations are responsible for this or flag the solutions in plotcal. For the delay rate, it seems to be noisy, but actually if you check the scale on the y-axis, this is picoseconds per second, and it doesn't even go beyond 1. So I'd be perfectly happy with this. So finally, we end up with the bandpass, and it was interesting. There was some discussion on this this morning, whether the issues with people seeing a slightly different plot from their data processing when they compared it to the EVN Jive tutorial, that might have been related to the bandpass. And this is a nice thing where you can demonstrate the power of the Jupyter notebooks. So I did the bandpass in the way it's described, and you get the plot. And I mean, then I did the way the bandpass is not described, and the only thing I changed here is the sol norm parameter here. So now I've set it to false, and you can see the plot here, clearly very different. There's a very different scale here on the y-axis than here on the y-axis. So here it's all around 1, and here it ranges from 3.5 to 0.5. So what is the difference if you apply this to the data? Was is indeed the trick. And if you apply all your calibrations, and I must admit, I don't know why I now have to scroll through the figures, because previously it didn't do that. But you can see this plot looks remarkably similar to what people posted in the MetaMost this morning. It has the big offset for the orange data here, stats here. And when I do sol norm is false, I have to scroll down a little bit further, then we get this plot. So it's same amplitude corrected versus frequency. And now I get the same plot that is shown in the tutorial. So the issue with that particular thing was the sol norm. And just copying and pasting these two cells in the notebook and rerunning them is sufficient to quickly check if that's indeed the case. So that's a nice thing about the notebooks, that you can easily compare the settings of a task, change one item, copy or just run it again and get the output immediately on your screen and see if that's what you're looking for. And once you're happy, of course, you save your notebook, and the next time you want to rerun it, you're done, and you have got exactly the same settings. So for Jive, this is really interesting, as one of our purposes in the longer term is that we can provide users not only with their data sets, but also with the pipeline processing that we've done. So you get a data set, and on the archive, for example, where you've got your FITS data and your associated calibration tables, you would also find a link to the notebook that was used to produce these results. So you can either reproduce them yourself or quickly have a look and optimize some of the settings to make sure that things look better and you have science-ready data. And at some point, you could even upload your notebook back to the Jive archive and say, okay, this is the notebook that I've used to publish the figure on this data set that I published in this Nature paper. So that makes things very helpful for us as well to optimize our data processing structure. So let me just quickly check if I've addressed everything I wanted to address in the notebooks. Yes, I did. So we're gearing up towards the end of the presentation. I'll go back and share my presentation again. There's a few remarks that I wanted to make here. So we've seen this, and if you download the presentation, all these links are active. So there's one warning, last warning, I cannot iterate this enough. The flagging in the apply cal will be iterative, so cumulative, sorry. So when you do the apply cal, and for example, there's some poor system temperature data or no system temperature data for part of your data, that data will be flagged, the visibility data that's associated with that part of your system temperature measurements. It will be flagged. This means that at some point, for example, in your instrumental delay calibration, the data will be noisier than expected. It will drop below your signal to noise boundaries, and such you get a sort of cumulative increase in noise or degradation of your data quality because of this, and ApplyCal will continue to flag more and more stuff. And I've seen it happen that people end up with no data or seemingly no data, which means that everything has been flagged and you basically have to start from scratch. Now this is fine. I've shown you at the point where I do the flag manager steps to make flag versions that I can revert back to when I start the calibrations from that point. This is something that you should not forget to do. It's always important to restore your flagging. And even 1 out of 5, 6 times that I do a rerun of the calibration, I forget to do this and end up with a mess. So restore your flags, make sure that you keep a good track of what you've been doing. And at some point, I have experienced this a few times, is when something corrupts either in the flag table or the measurement set. You get really weird things. If you plot stuff in your plotter mass and it looks totally not like what you would expect it to look like, it's always a good idea to start from scratch. And you can start at the point where you're importing your FITS IDI files into the CASA measurement set, you've already applied the system temperature append step, so you don't need to rerun that. But then you start with a clean measurement set and a clean flag table. So this is just for future reference for you. If you wanted to look at the notebook viewer, these are the links to it. And now we'll go and jump to the quiz. We've got about 10 minutes left, so I'll stop sharing my screen and hand over the screen share to Olga. And I hope she has also reiterated the event code. I'll put it in the chat as well. So if you can all go to the slide.do website, and the event code is M496, which are now listed in the chat. And I'll look up my questions here. Okay, so as people are joining, can we see how many people have joined yet, Olga? Or should we just go ahead and ask the questions? Okay. Oh, you can't see the figures very well. Yeah, there they go. So the first question to you. These are two figures that I just showed in the notebook, figure A and figure B. And this is part of the single band delay fringe fitting. So they both have the single band delay fringe corrections applied, and show you a bright source on the left side with the scan on the bright source for the calibrator. So what is problematic with, is there a problem with B? And let me properly, why does the instrumental delay not properly correct the phases for another scan, which is shown in figure B? So where is, I don't see the options for the answers yet. Okay. So the option is not bright enough, it's in a different location, or antennas have dropped out. Do we really only have 8 people participating at this point? Anyway, the majority is right. The figure B is the source in different location in the sky. Also, it's at a slightly different time, which affects your phase calibrations. Yeah. Okay. So the next question is getting slightly more complicated. I see that you've all been paying attention to the fringe fitting steps. So on the left, figure A is an uncalibrated file, uncalibrated data. On the right side, figure B has calibration applied. The question is, what is the difference between figure A and figure B? So which calibration has been applied to get to figure B? Is this the system temperature calibration? It's a bit of a trick question here. The single band delay fringe fitting calibration? Was it the bandpass calibration? Or is it the gain curve calibration? So what is the difference in calibration between A and B? Can you show the answers, Olga, or the people replying? Okay, so this was obviously already a little bit trickier. And as I was reading the answers back, I almost gave it away. There's a bit of a trick here. It both includes the system temperature calibration and the gain curve calibration, but the main effect that you see here is the gain curve, which normalizes your amplitudes to around 1. So answer A is almost right, but answer D, the last one, is really the correct one. Yay, we're starting to see people. Oh gosh, Harold is leading. Now there's a trick question. Okay, so up to the next question. There's 2 more. This is the before last one. So here you see a cutout from the list ops output. And the question is, all the information included is about the setup of your observation and what is the channel setup for a single spectral window in this case. So the answer options are there's 32 channels and each channel is 16,000 kilohertz wide. Or option B, there's 500 channels and each channel is 16,000 kilohertz wide. There's option C, there's 32 channels and each channel is 500 kilohertz wide. Or the last option, there's 32 channels and they have different widths. Yes, everybody has been looking very carefully, almost everybody looking very carefully. So the trick here is that the difference is between the channel width and the total bandwidth. So the total bandwidth is the sum of all your 8 spectral windows, but the channel width is actually the width of each channel. So each spectral window has 32 channels and each channel is 500 kilohertz wide and each spectral window is 16,000 kilohertz wide. Okay, last question. Here is a cutout from the GenCal output log. So this is what you would see in your CASA logger when you generate the calibration table for system temperature. What does this warning mean? So the options here are antenna 1 has missing system temperature data, but you can ignore the warning. Option B is antenna 3 has missing system temperature data, but you can ignore the warning. Option C is antenna 0 has missing system temperature data, but you can ignore the warning. And option D is this is a critical problem and you really need to fix your system temperature table. So what do people think? Time for the questions. Antenna 3 has missing system temperature data and you can ignore the warning, and that is correct. The number 1 in this cutout actually referred to the polarization and the number 0 referred to the spectral window, so that's obvious. And in all cases, these warnings are benign, you can ignore them. And if you are really getting concerned about this, just plot your system temperature table in Plot-MS and you can see if there's any issues there. So this was the last question for the poll. I'm really glad to see that people have been paying quite a lot of attention, especially to the fringe fitting step. That is something that is really tricky to comprehend. And that is the end of my presentation. So I'm ready to take questions. Thank you very much.
Yeah, thank you very much, Ilse. I almost threw my tea over my laptop. I was very enthusiastic. So you're in perfect timing. So let me see if there are some questions so that there has been a question, but it was already answered by Mark about the CASA pipeline. Is it supposed to replace Parseltongue APES pipeline, which currently is used to produce Jive standard output for users in the near future? And Mark replied for some definition of near. So he was very politically correct, on which the person who asked the question, Artis, said, near, do you mean a few years, 2 to 3?
I think that's a reasonable estimate. At this point, we've been working with the pipeline quite extensively for continuum data, but we're still in the process of verifying it for the maser line observations. So that is something that takes some time. And also to make sure that these things are overlapping at some point, we may start to release CASA pipelines data to the archive, but some users may want to have the APES pipeline as well to make sure that things are identical. All these kind of verifications are still ongoing. But it's at some point, we will have to slowly let go of APES.
Okay, that's a clear way forward. So there is somebody now typing yes, Yoon finished his question. Will the Jupyter pipeline keep tracking CASA release and make an appropriate update? So CASA releases every year or so a new.
Yes.
and the release? So this is a very good question.
Yeah, that's a really good question, and I didn't really address that here. The plan is after the workshop to start moving to CASA-6 and Python 3 also for the pipeline. And then we should indeed track the CASA releases. This is a bit tricky now at the moment for the current version of the pipeline because it's based, the Jupyter notebooks contain 5.6 and 5.7 was built by NREO on a different platform, so to say. It's slightly more complicated than that, but the bottom line is that including CASA 5.7 in the current Jupyter notebook environment was a lot trickier than expected. So we'd rather make that step in one go and go straight to 5.6 and then follow the releases from there. So but the idea is that at some point, because this is a Docker container environment, you can basically preserve the settings for the data processing that you've done for any particular data set. So you get your notebook, you get a version of this, the Docker container that we've run this in, or maybe even an exact copy of this. As you can tell, I'm not the expert on how this works in too much detail, but the idea is that you can reproduce the data processing that we have done in the pipeline environment on your own machine without having to install all these things. So if you have your data processed in CASA 5.5, that would be the version that's included in the notebook. If you would have the data processing in 6.2, that's the version that would be in the notebook, etc.
Okay, so every data reduction will be tied to a CASA version.
Exactly.
Which only becomes a problem in 10 years from now when we will have computers that can no longer run old CASA versions. These are problems that Alma is running into because the very early Alma data is working with the CASA version, which most of the computers cannot install. Well, the Alma regional centers still have them.
Actually, because the containers are supposed to prevent this from happening. As long as you can still run the container, it should work.
Yeah, but what Cassie is mentioning is currently for the older Alma data, the CASA versions still exist, but they are not containerized. So they're just standalone installs for Red Hat, very old.
Yes.
And most people don't run that anymore.
No, they can go to the Alma Regional Center, which have computer specialists that will then be forced to find this CASA version if it's not yet present and install it and run the data. But
yeah,
or it just needs to be passed through the new pipeline if it's feasible. So let me see if there are other questions. Let me see. Yes, we have another one. How long does it take to reduce the data through the pipeline? Taking an average, I don't know, 8-hour, 12-hour EVN data set?
Yeah, well,
10 antennas?
I actually did this just last night for the N14C3, but obviously this depends on the system that you're running your data processing on. So on my own laptop, the notebook that I just showed, the N14C3, takes about an hour. If I would do this on one of the Jive development machines, it would easily speed up things by a factor of 3 to 4. So it mainly depends on the memory, but also the possibility of faster CPU access. The CASA has the option to use multi-threading, the MPI package, and Jack told me offline that he's been able to activate this and now speed up things significantly, especially the appendices, for example. It takes a couple of minutes on my laptop. He reports that it can be done in 10-15 seconds with the MPI package.
So there is a specification to the question. What's the volume of this data set in gigabytes?
The N14C3 is 2.5 to 3 gigabytes.
So that's for EVN, it's a rather small data set.
We are now starting to play with the spectral line data. They are orders of hundreds of gigabytes. That's because of the spectral resolution in these data sets. For continuum data sets, you're usually not exceeding a couple of gigabytes per data set.
10 gigabytes is sort of standard for a continuum data set.
All right, we have other questions in the Jupyter notebook. Is there any hard limit on the memory requirements specific to VLBI and EVN data of the machine? Do you have a number?
Not from the top of my head, actually, and I must say that although this was an issue in older CASA versions, I've not had that problem in recent years. So I know that the CASA developers have been looking into making a task that could quickly check if your laptop is suitable to run CASA for certain data sets, but that never really materialized, mainly because users no longer ask for it. So it's hard to give numbers here.
Yeah, I know there is somewhere on the NRAO CASA website the specifics of the computer on which to install CASA. Yep. So if I find back the link, I will place it in the Jupyter Notebook.
Yeah, I think it's on the download page. They have some guidelines.
Yes. So then we have two more questions. One from Mustafa Yildiz. Some of the tasks use parallel programming, as you already mentioned, MPI CASA, but some tasks use only one core. Do you know if there is any planning to upgrade these single core tasks?
Well, actually, for CASA 6, not a whole lot will change, but there are already plans for beyond CASA 6, where everything will be completely parallelized. So all tasks will be parallel, and the current issue with CASA is that some tasks have options to do parallelization, and they follow a different code path from the singular performance in that same task and can sometimes give different results. So this is a big issue for the ALMA pipeline, for example. So for the future, and then I'm talking about 5 to 10 years easily in the future, a next generation package will be developed, which is completely parallel. NRAO now calls this next generation CASA, and they've been advertising this in platforms such as the ADAS, the astronomy software meetings, where they look for feedback from people at the development level. But I think in a couple of years, they will start to be more vocal about this also towards the users. But it will be a while.
Okay, thank you, Ilse. Then I have one last. Oh, sorry. Yes.
Just to add on that question very briefly, is that actually even if a task is there right now which does not run in parallel, you can always directly interface with the MPI option in CASA and just manually run it in parallel. That's, for example, what I did with the fringe fit task. It just requires some extra coding, but if you need that speed, that's easily possible with every task.
Okay, thanks for that addition, Michael.
Yes, thank you, Michael. So I will go into the last question, if nothing else comes up. So Miguel is asking, will Jive make fast computers locally at Jive available to run remotely these Jupyter notebooks, at least for the PIs of, say, the last 2 to 3 years?
Yes, but I have to look with a sort of slanted eye at Mark. The idea is that we are going to host a Jupyter Hub. And from what I understand, this is exactly what is intended. So a PI can access the hub at Jive, process their data on our machines, and make sure that it's optimized for the science that they want to do with this, and hopefully also provide us some feedback. And doesn't need to do this on the local machines. That's correct, right, Mark?
Yeah, well, what's currently funded, we're doing this in a project called Escape. Starts with an E as well, which is sort of trying to bring, people might have heard about the European Open Science Cloud. And this is sort of the astronomy contribution to that platform. And as part of that, we are developing this Jupyter Notebook infrastructure. And within that project, we have money to get one server. So that might be good enough for a part of the PIs, but maybe not for all of our PIs. Then we need to extend that infrastructure, and then we need to find money for that.
Yeah.
Yes, it is at least, we're planning to do at least a demonstrator of this functionality that will be accessible to the people that want to use it, the PIs, EVM PIs that would want to use this.
Yeah. Yeah, like with all these kind of developments, you don't want 100 people to start using it in one go before you know that it actually works.
And yes, that has indeed the benefit that getting the data from the archive will be almost instant. because the machines will be sitting very close together, and it will be a fairly powerful machine, so you won't run out of memory. But some people will still, we anticipate that some of the PIs will still prefer to do the data reduction on their own machines.
And some will still prefer to use apes 10 years from now.
Yeah, everybody does what they like best.
Exactly.
So I have the feeling that we have exhausted the questions for now. I advise people, if more questions come up for Ilse, please put them in the notebook. The same also for Ivan of the typical data problems. And I would say let's close this session here. Thank both our speakers, Ivan and Ilse, for 2 very nice talks. And reconvene for data processing C at 1600 hours UT.
Yes.
Yes.
If you allow me to make one announcement, is that I fixed the append thesis script for spectral line data sets. So if you checked it out using Git, you can simply run git update to get it, or other download a new zip file with the scripts and run those. If you don't have spectral line data, you probably don't need to do anything.
Excellent, that was super fast. That's really on the fly problem solving. Thank you, Mark. Yeah, I see also Mateusz is very, very happy with that. So thank you, Mark. Thank the speakers, and thank to all the attendees and everybody who interacted on the various platforms.
Thanks.
See you at 1600.